Good morning, my name is Manishankar Yadav and today I will explain the basics of the electronics devices and circuits. Then basics of electronic devices and circuits. Every electrical and electronics engineer should know about the basics of the electronic devices. Then what is the basics? First one is the energy gap, also called as the EG. Second one is the energy band diagram. Energy band diagram. Energy band diagram for conductor, semiconductor and insulator. Third one is the mobility, also denoted as a mu. And fourth one is your resistivity. And fifth one is your conductivity. These 5 basics points I will explain today. There are many more points are there, but I will explain only these 5 points briefly to all of you and one by one. And this your first one is the energy gap. What is energy gap actually? Energy gap is the difference between maximum of the valence band and the minimum of the conduction band. You can see here, this is your energy axis, this is your momentum space or K space, and this is your valence band and this is your conduction band. And the difference between the valence band maximum and conduction band minimum called as a energy gap, EG. It's denoted by in a unit of your energy gap is electron volt. Means this much energy required to electrons jump from the valence band to conduction band, so that conduction will be possible. Okay. And for EG, for semiconductor, for germanium and for silicon at 0 degree Kelvin, this is for 7.85 electron volt, 1.21 electron volt, and the energy gap at 300 degree Kelvin you will find for germanium 0.72 electron volt and for silicon 1.1 electron volt. You can see from this two energy at a different temperature energy gap. This is energy gap inversely proportional to your temperature. Okay, you can see if energy gap decreases with increase in the temperature. Okay. And this is relation between your energy band and your temperature. For at any temperature, your EGT is equal to EG 0 degree Kelvin minus beta T. What is the beta? Beta is your material constant. This is depends on your material. Okay. Then second part is your energy band diagram for the 3 types of the material: conductor, insulator, as well as for semiconductor. Okay. Then energy band diagram. Okay. First one is conductor. What is the meaning of conductor? Conductor means at a 0 degree temperature, even at a room temperature or 0 degree or absolute temperature, also it has free electrons which will conduct without giving any energy. Okay, free electrons are available. Free electrons are available at 0 degree Kelvin. Okay, and this is your energy band diagram. This is your energy axis, and this is your EV here, and this is your AC. This should overlap for the conductors. These two EV and AC are overlapped. Means free electrons are available at the conduction band of the conductors. Okay, here free electrons are available to conduct. This is also called as positive temperature coefficient, because if temperature increases, then mobility decreases. That's why means resistivity increases. Positive temperature coefficient also is called. If temperature increases, then resistivity increases. Okay. Example: copper, gold, silver, etc. Okay. These are the what is your conductors. Okay. And second one is your second one is your insulator. Okay. It's very interesting property. Insulator. Okay. Even insulator means that even there is no free electrons even at a room temperature. This is your energy, and this your conduction band, and this is your valence band. See, this is your energy gap is very high. Energy gap is nearly to or equal to 5 electron volt for insulator. Okay. This, suppose for insulator, if you increase the temperature, slightly, if temperature increases, Eg slightly decreases. Okay, then Eg inversely proportional to temperature. This increases means this decreases. Okay, and this is also called as the negative temperature coefficient. Okay, then temperature increases means resistance decreases. Okay, there is no free electrons at absolute 0 temperature as well as your room temperature also. Okay, suppose this is your example: wood, diamond, mica, SiO2, air. All these are the your example of the insulators. And most interestingly, your semiconductors showing up in between behavior, like say your insulator and conductor. Semiconductor. In semiconductor, what happen? This your energy gap is your small, about 1 electron volt. This is your AC, this is your EV, this is your energy axis. Okay, and see, in semiconductors there are covalent bonding is there, and if you temperature increases, then what happen? Energy gap decreases, then electrons from here to here jump. Okay, if temperature increases, but at absolute temperature there is no free electron. It behaves like a insulator, behaves like insulator. Okay, but if temperature increases, resistivity decreases. This is the negative temperature coefficient. Okay. An example you know already, silicon and germanium. Why carbon is not a semiconductor? Why? Because carbon also have a 4 valency. Why carbon not behaves as semiconductor? Okay, first point is graphite, carbon allotrope, behaves like conductor. And second point is what? Your diamond. Diamond behaves like insulator. Because of the unstable structure of the carbon, it's sometimes we have like a conductor and sometimes we have like insulator. That's why we are not considering carbon as a semiconductor material. Okay. And what is the advantage of germanium and silicon? It's depend on the application. Okay. Why we are using mostly silicon? There are many reasons. Okay, to consider silicon as a mainly for application, because it has abundant in nature. Second point, it has very low leakage current. High range of temperature variation. You can use for a large range as compared to germanium. This one main reason is that it has a very low leakage current in the order of the 10 to the power minus 9 means in nanoampere leakage current. But in case of germanium, this is 10 to the power minus 6 means this is the your microampere. This is very high as compared to silicon. That's why mainly you are consider a silicon as your for your application. Okay, this is clear why you are using silicon as compared to germanium. Okay, then third point is your mobility. What is your mobility of any material? Mobility denoted by mu. Mobility means how fast electrons or holes moves from one place to another place in your material or in your semiconductor. You can say holes and electrons in case of semiconductor, how fast they are moving. Okay, this is your mathematically related as your drift velocity upon electric field intensity. Okay, what is your drift velocity? In the presence of the electric field, velocity attained by electron or holes called as a drift velocity in the presence of your electric field, external electric field. Okay, this is your drift velocity upon electric field intensity. Okay, drift velocity denoted by Vd, and electric field denoted by simply E. Okay? Vd is velocity is meter per second. Okay, meter per second or centimeter per second. Your drift velocity. And your electric field, what is the electric field? Is proportional to V by D, means voltage by meter. Okay, voltmeter or volt centimeter. Okay, then what is the unit of mobility? See, your centimeter square upon second into volt. Okay, this is your unit of mobility. Okay, mobility depends on the drift velocity as well as electric field intensity. Okay, you can see your mobility depends on your material, which material you are using. Suppose for semiconductor, or germanium and silicon. Okay, mobility of electron, this is 3800 centimeter square on second into volt. This is your 1800 centimeter square upon second into volt. Okay, and this is your 1400 for your holes, centimeter square upon second into volt, and this is your 500 approximately centimeter square upon second into volt. It's depend on the material, what is your mobility. Okay, in case of germanium you will find a very high mobility, but you can increase your mobility in silicon also with a different method are there. You can increase the mobility. Okay, and how mobility changes with the electric field, applied electric field. Okay, this is your mobility, this is your electric field. Okay, till here this is constant, till here this is also constant. 10 to the power 3, 10 to the power 4, and again E. Your mu must be proportional to 1 by under root E. In this case, mu proportional to 1 by E. Okay, and here it's very high electric field, you will find a small mobility. Mu naught. Okay, for this reason 10 to the power 3 volt per centimeter, 10 to the power volt per centimeter. This electric field you will find a constant till here. After that you will inversely proportional to 1 by under root E. After that mu proportional to 1 by E. Okay. Mobility depends on temperature also. If you increase the temperature, so if you increase the temperature, mobility decreases. Okay, then mu related to E by minus m. M is material constant again. Material constant. Okay, this is your mathematical relation between temperature and your mobility. It's very interesting. You will further, if you study, then you will find this play a very important role in the electronic devices and their performance. Okay, the drift velocity also is a main parameter. Suppose V and your this Vd, you will find from here this type of graph between. This is your linear region, this is your sublinear region, and this is your saturation region. For a very high electric field, you will find your drift velocity will be saturated. Okay, this relation you should know. This is very important for your further consideration. Okay, for numerical solving problems. Okay, this is your mobility. And again, one interesting parameter coming, resistivity. Resistivity is opposite the flow of current, you already know. Okay, then this is the brief introduction. Resistivity R is equal to rho L by A. This depends on the, this is the resistance, this is the resistivity. Then if you see, resistivity is equal to R A by L. This depends on the your length of the wire. Okay, and resistivity with temperature, if we increase the temperature for a semiconductor, okay, then resistivity decreases with temperature increases. Okay, and for metal you will find a opposite behavior. For metal, if your temperature increases, then resistivity also increases. Okay, and this is the, what is your resistivity, ohm meter or ohm centimeter. Okay, this is the unit of resistivity. Okay. And last one is your conductivity of any material. How conductivity you can control. Conductivity denoted by your sigma. Okay, then what is the conductivity of any material? Carrier concentration into your charge into your mobility. Mobility plays a very important role. I already told you what is the importance of mobility. You can see further in your this electronic devices subject. Okay, then your conductivity for any electronic devices, conductivity plays a very important role. Okay, then carrier concentration into charge into mobility. Okay, this is your fixed, but this carrier concentration and mobility plays a very important role in for any conductivity of any material. Okay, then mobility, if mobility is high, then your conductivity is very high. Then it's very important for your electronic devices. Conductivity should be smooth or very high for electronic devices, as well as for different applications of electronic devices like switching purpose. Okay, and carrier concentration denoted by rho, mobility denoted by mu, and this your charge denoted by n. N or Q, you can say anything, Q, and this your concentration of carrier, concentration N. Okay, this is sigma. This is for your, in case of metal. Suppose if you have a semiconductor, then sigma, you will have two terms. Charge is constant, and for your n-type material, suppose for electrons, this is n and this is mu n plus p, and this is for your mu p. Okay, and this is your constant, and this is your conductivity. Okay, conductivity depends on the depends on your temperature, conductivity depends on temperature, mobility, carrier concentration, okay. Then these three ways you can control the conductivity, okay. According to your application, you can, for high temperature or for low mobility or high mobility or carrier you can doped with a different carrier concentration. I will tell you the in next class about all these in details, okay. These are the basics you should know. Every electrical or electronics engineer should know the basics. These are the basics. Without this, it's very difficult to understand the electron devices subject or analog in details if you will go further. Okay, thank you very much. ऑफ कैसे होगा लेकिन बहुत बड़ा 26 मिनट होगा